This is a greetings from Professor Quill to the scientific community at large, or the unscientific community, as it may. It's come to my attention that a certain conspiracy regarding the topological nature of our home planet has been making its merry jaunt around town. Indeed, some people actually think that the Earth is flat, and I find it my personal duty, as an esteemed intellectual, to nip this cute little assertion in the bud before it gets away with pilfering any more of my remaining brain cells. So, my friends, I ask you to please heed my word on this day. Not as any kind of scientific authority or innovative philosopher in the field, but rather a humble man with nothing but his whiteboard, an expo marker, and a dream that maybe even these misguided conspiracy theorists could achieve ownership of their own brain cells one day. And thus begins my proof that the Earth cannot possibly be flat. Let's do this. So the first point that I'd like to make in this proof is that whether the Earth is a flat disk or a sphere, there has to be a circular cross-section that we can cut out of it and consider in the two-dimensional plane. Now, the two most important characteristics that we have to consider when we're talking about circles are perimeter, otherwise known as circumference, and area. The circumference of a circle is given by 2 pi r, and the area, similarly, is pi r squared, where r is the length of the radius. Hold on to that thought. Now, this is the part of the proof where I start to draw shapes. This is a triangle. On the other hand, this is a square. This is a pentagon, hexagon, heptagon, octagon, Kazuma-Kuwabara, nonagon, decagon. Now, you probably noticed that as I increased the number of sides of these regular polygons, they begun to look more and more like a circle. Indeed, this is actually a mathematical fact that as you take regular polygons and as the number of sides approaches infinity, the resulting shape approaches that of a circle. And in fact, there is a very mathematically rigorous and precise way to express this idea in terms of perimeter and area of these regular polygons. Since the perimeter of any regular polygon is the number of sides times the length of each side, we can say that the limit as the number of sides, n, approaches infinity, of n times s, where s is the length of each of the sides, well, that should approach the circumference of a circle, which is 2 pi r. And by that same token, the area of these polygons should also approach pi r squared as the number of sides approaches infinity. But of course, that begs the question, how do we write the area in terms of the variables that we already defined? Well, you can imagine that as we break these polygons into triangles, then if we find the area of one of these triangles and then multiply by the number of sides, that should equal the total area of the polygon. Define this side length as s, and the height of the triangle is denoted h. Now, if we consider this a right triangle, where the legs are given by s over 2, since we're splitting the side in half, and h as the other leg, then the hypotenuse of this triangle would be precisely r, the very same radius as in the circle. And since this is a right triangle, we can use Pythagorean theorem to say that s over 2 squared plus h squared is equal to r squared. And after a few algebraic manipulations, we can see that h is equal to the square root of r squared over s minus 2 squared. And knowing that the area of a triangle is 1/2 base times height, we can say that the area of the overall polygon is the area of the triangles, 1/2 base, which is the s, times the height, which we just found to be square root of r squared minus s squared over 4, and then times the number of sides of the polygon. In other words, n. And similarly, if we take the limit as n approaches infinity of this expression, we should approach the area of a circle, which is pi r squared. But notice that we can actually pull out this 1/2 times square root of r squared minus s squared over 4 because those terms do not depend on n. So we can actually pull those outside of the limit. And what are we left with? We're left with 1/2 square root of r squared minus s squared over 4 times the limit as n approaches infinity of n times s, wait a second, that's exactly what we got up here, which is 2 pi r. Substituting that into the equation, we get that this is equal to 2 pi r, and then we can start to see some cancellations. The 1/2 and the 2 will cancel out, and then we can also divide both sides of the equation by pi r to get rid of one of the r's on this side, and then one of the r's on this side, and we can see that the square root of r squared minus s squared over 4 is equal to r, with some negligible expo debris left over. And squaring both sides, we can see that r squared minus s squared over 4 is equal to r squared, and subtracting both sides of the equation by r squared, we can see that s squared over 4 is equal to 0, which implies that s is equal to 0. But remember what s was. S was the length of the polygon's sides. My dear colleagues, the Earth is not flat. No, it's much worse than that. The Earth is a stick, and if anyone dares to challenge the validity of this proof, please, I beg of you, send me a DM of your hands caked in black charcoal expo ink, and maybe, I will take your word seriously. I just realized something else. I just realized something else. If s is equal to 0, then the limit of ns has to be the limit of 0 as n approaches infinity, but that would mean that 2 pi r is equal to 0, but that would mean that r is equal to 0, but that would erase the rest of... It's just a single point. The Earth is a singularity. I need to make some calls.